Welcome once again in the class of topology and in the lecture of compactness, the covering spaces. In the previous video, I have told you about the finite intersection property, about the arbitrary intersection property. I have also told you about the Bolzano-Weierstrass property, but I am restarting here from the Bolzano-Weierstrass property because I'll need this property now to prove the results we are going to prove today. So, a topological space is said to have Bolzano-Weierstrass property if every infinite subset of it has a limit point. That is Bolzano-Weierstrass property. And if a topological space have Bolzano-Weierstrass property, then it is known as Freche compact space. What is a Freche compact space? It is a topological space having Bolzano-Weierstrass property. So, the first theorem we are going to prove today is that it is theorem in which it states that prove that every compact space has Bolzano-Weierstrass property. That means every compact space is Freche compact space. In other words, you can say. So this we will prove first, and then we will move further on to the next theorem, that will be nested closed interval property or nested closed interval theorem, you can say. So before going on to that theorem, let us move on to the proof of this theorem first. So let X tau be a compact space, and we want to show that it has that Bolzano-Weierstrass property. That means every infinite subset of it has a limit point. So on the contrary, suppose that there is an infinite set which has no limit point in it, and then we will arrive at some contradiction, which will mean our supposition is wrong, and hence every infinite subset of X will have a limit point. So let, if possible, there be an infinite subset A of X having no limit point. Let X be a point of X. Since A has no limit point, X can also not be a limit point of A. And if X is not a limit point of A, then there exists a neighborhood of X which will have not more than one point with intersection with A. So therefore, there exists a neighborhood Nx of X such that Nx has at most one point of A. Now collect all these such neighborhoods for every point X belonging to the space X. Consider C is equal to all such neighborhoods Nx for every X belonging to the space X. Obviously, Nx is neighborhood, so it is an open set, and for every X belonging to X we are having, that means their union will cover X. So this C is an open cover of X. Then C is an open cover of X, but your X is compact, and if a space is compact, then for every open cover you must have a finite subcover. So here once again you are having C as an open cover of X and X is compact, so you must have a finite subcover of it. So therefore there exists a finite subcover C star. Members of C star will come from C because C star is a subcover of C. So members of C star will be nx1, nx2 and so on, nxn. So this is a finite subcover of C and C was open cover of X. So that means union of these members will cover X. So X is equal to, because X is the whole space, so I can take equal to, I may not write subset of, so X is equal to nx1 union nx2 union nx3 and so on union nxn. Now A is a subset of X. A is a subset of X. So that means you can directly say that X is a subset of this union. But every nxi has at the most one member of A. So nx1 has at the most one member of A, nx2 has at the most one member of A, nx3 has at the most one member of A, nxn has at the most one member of A. That means this union can have at the most n members of A. That means A cannot have more than n elements. That means A is a finite set, which is a contradiction. Why? Because A is given to be an infinite set. An infinite set cannot be a subset of a collection such that each one from this collection is having at the most one element of that set. So this is not possible. This is a contradiction. So this is a contradiction. That means our supposition was wrong. And what we have supposed that A has no limit point, so A must have a limit point. That means every compact space has BWP, Bolzano-Weierstrass property. Then I am going to prove another theorem which will be helpful in proving another result in future, when we will prove that every closed interval on real line is compact. A result will be needed, and that the result I am going to prove now. So write down the theorem. This theorem is also known as nested closed interval theorem. Nested closed interval theorem. If In is a sequence of closed intervals such that In is contained in In plus 1 for every n belonging to n, then intersection of In where n belongs to n definitely is not phi. This theorem is known as nested closed interval theorem. So this theorem we are going to prove now, because it will be used in the next theorem, where we will prove that every closed interval on the real line is compact. So before that, we will prove nested closed interval theorem. So we are given that let In be a sequence of closed intervals with In subset of In plus 1 for every n belonging to n. That means what you are having now, this is your real line. You are having I1. Suppose this is your I1. Since put here n is equal to 1, your I1 is a subset of I2. it must be on the other way. In must contain in plus 1. In the previous one, where I have written in is a subset of in plus 1, please make correction. In must contain in plus 1. So here I1 contains I2. So that means I2 is somewhere here. So let it, the first one be A1, B1. Let the second one be A2, B2. Then I2 contains I3. That means A3, B3. Then I3 contains I4. That means A4, B4, and so on. Now, look carefully. You are having two sequences. One sequence is AN and other sequence is BN. Your AN sequence, it is monotonically increasing and is bounded. Your BN sequence is monotonically decreasing and is again bounded. Why bounded? Because every AN is less than B1, or in fact every AN is less than every BN, you can say, and every BN is greater than every AN, so BN is also bounded. This sequence is bounded above and this sequence is bounded below. From your knowledge of sequences and series, you know that if a real sequence is monotonically increasing and is bounded above, then it is convergent, or you can say then this sequence has least upper bound or supremum, whatever you want to say. So this sequence has least upper bound or supremum, and supremum of AN or least upper bound of AN, let it be A. Let it be A. So A will be something over here. A will be here. This sequence is monotonically increasing. Since A is your LUB, least upper bound, that means every AN is less than or equal to A. So this means every AN is less than or equal to A for every N belonging to N. Once again, every AN is less than every BN. That means every BN is an upper bound for this sequence. B1 is an upper bound of AN, B2 is an upper bound of AN, B3 is an upper bound of AN, B4 is an upper bound of AN, and so on. Every BN is an upper bound of AN. And A is least upper bound. This is least upper bound, and every BN is an upper bound. You know that least upper bound is less than or equal to every upper bound. So that means A is less than or equal to BM for every N. So since every member of this set B1, B2, B3 and so on is an upper bound of the sequence AN, and A is least upper bound. We know that least upper bound is less than or equal to every upper bound. So this means your A is less than or equal to every BN. So that means here you have written that AN is less than or equal to A, and this A is less than or equal to BN for every N. AN is less than or equal to A. This is because A is the least upper bound of the sequence AN. And A is less than or equal to BN because A is the least upper bound and every BN is an upper bound. So that means AN is less than or equal to A is less than or equal to BN for every N belonging to N. And look carefully, it means A belongs to the interval AN BN for every N belonging to N. And this AN BN is the interval IN. So A belongs to IN for every N belonging to N. And if A belongs to every IN, then why can't I write A belongs to intersection of IN where N belongs to N? And this directly means that intersection of IN, N belonging to N is not phi. and that is what we wanted to prove. So what we have proved that if we are having a sequence of closed intervals of the nested form, now nested form means In contains In plus 1. So if we are having a sequence of closed intervals in nested form, then their intersection is not phi, and that is what we wanted to prove in this nested closed interval theorem. So I'm going to stop this video here. In the next video, we'll prove that every closed and bounded interval on the real line is compact. Thank you. Thank you once again.